This is my LabVIEW VI block diagram to calculate the junction capacitance for a reverse bias PN junction. If you look over here to the left, you will see the five input blocks. And if you double click on one, it takes you to the front panel, which shows that all five of them have default values already entered in. The top is the temperature in degrees Kelvin. The next input is CJ naught, which is the capacitance at zero reverse bias. And then we have NA and ND, which are the concentrations of acceptor atoms and donor atoms for the PN junction. And then VR, which is just the potential of the anode with respect to the cathode. And that is negative when reverse bias. So I just set the default value for it at -1. If we hit run for the code at 300 Kelvin, that gives us a thermal voltage here shown on this indicator of 2.5875 times 10 to the -2 volts, which is 25.87 millivolts, very close to the approximate value of 26 millivolts given for the thermal voltage at 300 Kelvin. So we know that the code is calculating correctly. If we go back to the block diagram, we feed the temperature firstly in degrees Kelvin to this sub VI, VT sub VI that calculates the thermal voltage. And if we double click that, it shows that it takes the temperature as an input as well as K, which is the Boltzmann constant, and multiplies those together and then divides that value by E, which is the magnitude of the charge of an electron. If we double click that, it shows that K and E have their values indicated here. And then the thermal voltage is shown on an indicator for the main VI, and it is also an input into this next sub VI, which calculates VBI, which is the built-in potential of a PN junction. That also takes the NA and ND quantities as inputs. And if we double click here, you can see that the NA and ND are multiplied by each other, and then that quantity is divided by the square of Ni, which is the intrinsic carrier concentration of silicon. And then the natural logarithm here is taken of that quantity and then multiplied by the thermal voltage, and that gives you the VBI value here. And finally, on the last sub VI, the junction capacitance is calculated. It takes the VBI as an input as well as VR and CJ naught. And if we look at the block diagram for that sub VI, you can see that VR is divided by VBI, and then that quantity is subtracted from 1, and then that result, the square root is taken of it, and then 1 is divided by that value. Basically, this section of the blocks here that I've highlighted calculates the -1/2 power of the quantity of its input and gives that as output. And then that value is multiplied here by CJ naught to give the final CJ value of the junction capacitance. And the whole block diagram is put as a while loop, which lets you run the code and continuously change any of these inputs, primarily the temperature, but if you wanted to, you could change the acceptor, donor concentrations, or the VR value. and you get real-time results here for the thermal voltage and the junction capacitance.